In the last video, I talked about wind and how wind pushes sand into sand dunes and creates some desert landforms. In this video, I want to talk about the causes of aridity, right? So the origin of deserts, why are different parts of the world dry and have desert landforms? And then we'll talk a little bit about desert landforms in general. Okay, so there's a couple of reasons for the origin of deserts. One of them is zones of atmospheric high pressure. So we have these persistent bands where air is typically moving in a downward direction, right? It's descending from aloft, and that creates high pressure in areas with very little rainfall. Here's a diagram, and there's a similar diagram in your textbook that shows this atmospheric circulation, but the best way to learn it is to draw it. Okay, so you can pause the video now and go get yourself a piece of paper and draw this. So here's the planet, and I've labeled a few key lines of latitude: the equator, 30 degrees, 60 degrees, and 90 degrees north and south. So go ahead and pause the video here, get yourself a piece of paper and a pencil, or even like a couple colored pencils, and we'll draw this. I'll wait. Okay, hopefully you've done that and unpause the video now. So let's talk about why there are certain areas of high and low atmospheric pressure. Well, let's say we have the sun over here. If I can draw this on here. Here we go. So this is the sun. This is not to scale. The sun is very, very far away. But in general, the way the Earth orbits the sun, we have very intense solar heating near the equator, between the tropics, right? So between about 23.5 degrees north and south. And this is where, if the sun's rays hit, it's going to be focused on a very small area because the solar rays are hitting very close to a 90-degree angle. When you get up here at higher latitudes, either north or south, the area of sun's rays are spread out over a larger area because of the curvature of the Earth. So the heating is much less intense. So because we have intense heating here, I'm going to erase some of these to give myself some more room. Because we have intense heating near the equator, the surface of the Earth heats up, and that warms the air above the surface of the Earth, and so the air rises. And so if we have rising air near the equator, now these are the arrows you can draw. If we have rising air near the equator, we call that an area of low pressure, right? If you ever watch a weather forecast, you see a little map with H's and L's for highs and lows. So low pressure means we have rising air. If we have rising air, the air rises up into the higher atmosphere and it cools. And when air cools, it condenses into clouds and we have precipitation. So areas of low pressure, L's on the weather map, mean that you have rain and precipitation. Now, so that air is rising in areas where we have intense solar heating, like at the equator. Now that air, when it goes up, it spreads out, right? Because more air rising pushes that air out of the way and it spreads out, and then it cools off. When it's up in the high atmosphere, that air is cooler, cold air is more dense, so then that cold air will sink. And so we tend to get sinking air around 30 degrees north and south of the equator. So around 30 degrees north and south, we have descending air, and those are areas of high atmospheric pressure, air pushing down. Right, so we have H's, high atmospheric pressure at 30 degrees north and south. All right, let's go up here to 90 degrees. So at the North Pole, 90 degrees, again, we have sinking air here because it's very cold, right? It's very cold at the poles, 90 degrees north and south, right? So air descending is high pressure. So we have high atmospheric pressure near 90 degrees. Right, high atmospheric pressure. Okay, now that air that's descending, it hits the surface and it spreads out, so it goes this way. And we have descending air at 30 degrees, and that spreads out. So when we get up here to around 60 degrees, these two areas of wind, areas of air masses, are converging, and so they have nowhere to go but up, right? So there we have rising air because of these air masses being forced together, and that's low pressure, right? Rising air is low pressure. So again, around 60 degrees north and south, we have an area of lots of precipitation, right? We have cold air and we have rain and snow and all that stuff. And these form cycles, right? So as the air rises aloft and it spreads out, and so we get this kind of setup. I won't draw it down in the southern hemisphere, but the same thing in the southern hemisphere, area of low pressure around 60 degrees. So you see what we have here, 90 degrees, you have high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. Okay, now air moves from areas of high pressure to low pressure, right? If we have descending air, that air is piling up and it's descending and it pushes out and it flows towards areas of low pressure. So I'm going to use green here. And so in these bands of, between these bands of latitude, we have air moving from high to low, but then we have deflection. And so if you look in your textbook, there's a description of Coriolis effect. Coriolis effect bends winds, or the apparent path of a wind, in a certain direction. In the northern hemisphere, it deflects winds to the right, and in the southern hemisphere, it deflects winds to the left. And that's basically because the wind is moving and the Earth is spinning underneath, and so by the time the Earth gets to a certain point, the Earth will have turned, and so you get these what looks like a curved path, but it's actually a straight path. There's lots of great videos and things online you can see, including in your textbook. There's a nice animation to understand Coriolis effect. But let's consider this. Okay, so from 30 degrees north to the equator, the winds are going from high to low. And like I said, in the northern hemisphere, the winds are deflected to the right, to the wind's own right. So if my wind is going from high to low and then it's deflecting, its path is deflecting to its right, the path of the wind looks like this. So between 30 degrees north and the equator, the winds are doing this thing. In the southern hemisphere, from 30 degrees south, again, we're flowing from high to low, and in the southern hemisphere, the winds are getting deflected to their left. So the path of the wind is like this, right? And then you can draw these in on your own and really kind of get an understanding for these winds. From the North Pole, from 90 degrees, we're going from 90 to 60, so high to low, and again, the winds are getting deflected to their right. So we go like this, right? The path of the winds here are like this. From 30 degrees north to 60 degrees north, again, they're going high to low and deflected to their right. So here the winds are doing this in the northern hemisphere, right? And then in the southern hemisphere, the same thing, from high to low and deflected to their left. From 90 to 60, the winds are doing this. And then from 30 to 60, from high to low, deflected to their left, the winds are doing this. All right. So we have these bands of winds where the winds move either eastward or westward. Now we label winds from the direction they come from. So in the northern hemisphere here, these are easterly winds. In fact, we call these the northeast trade winds. All right, trades. We call those the trade winds. In the southern hemisphere, we call those the southeast trade winds. Trades. Great writing. But then between 30 and 60 degrees, these are our belts of westerly winds. We call these the westerlies. Westerlies. And we have another belt of westerlies up here, right? We label the winds from the direction they're coming from. These winds are coming from the west, so we call them westerlies. Near the poles, these are easterly winds, so we call these the polar easterlies. Easterlies, anyway. And then again, we have polar easterlies down here too. Okay, so that's the general circulation of the atmosphere. The important things to consider is where you have wind, where you have high pressure, areas of high pressure are dry, right? So I'll draw a little saguaro cactus here. So 30 degrees north and south, we have these persistent dry areas of high pressure. And then the winds are primarily coming from the east or the west, depending on which latitude you're at. Now, the direction of the wind matters for the origin of deserts because let's say you have a mountain range blocking the way. We have the creation of what's called a rain shadow effect. So here we see if we've got air coming this way off the ocean, that air has got a lot of water in it because of evaporating water off of the ocean. And if it hits a mountain range, that air is forced to rise. It has to move up over the mountain range. As it goes up in altitude, of course, it gets colder, and colder air can't hold as much precipitation. So as it moves up, it gets colder because it's cooler temperatures higher up, but also that air is expanding because there's fewer molecules of gas up here than there are down here at sea level. So there's fewer molecules of gas pushing in, so the air expands, and expanding air cools. That's just a law of physics. If you've ever let the air out of somebody's car tires, because that air is compressed in the tire, and then you let it out, that air feels really, really cold because that air, the gas is expanding. So the gas is expanding as it moves up in altitude, so it cools, and so we get condensation, we get cloud formation and precipitation. So the windward side, the west side of this mountain range, is very wet because we have a lot of precipitation. Now, as you come down the other side of the mountain, that air is descending, and so as you compress air, it heats up, and hot air can hold more moisture in it than cooled air, so we're not getting any condensation or precipitation. Again, if you've ever pumped up a bicycle tire with a hand pump and you feel the cylinder gets hot, the cylinder of the pump, because you're compressing that gas and you're warming it up. So coming down the back side of this mountain, the east side, we have warm, dry air because you're compressing that air, and a lot of the moisture has already fallen out back here. So this is called a rain shadow. And here's another example of that. So the Sierra Nevada range in California is a great example of a rain shadow. Air coming off the Pacific Ocean is moist, gets pushed up over the Sierra. They're very high mountains. The west side, we have rainforests like this because of a lot of precipitation, and the dry side, we have the Great Basin Desert over here that's very dry. So your assignment for this week, or one of your assignments for this week, is to do, you're going to look at the different deserts of the world, and you're going to give an explanation for why each one is dry. So you have to think about, is this an area that's close to 30 degrees north and south? And if so, it's probably influenced by this subtropical high pressure, regions of high atmospheric pressure that tend to be dry because we have descending air. Another reason is it could be in a rain shadow, right? So if you have westerly winds coming between 30 degrees and 60 degrees, and there's mountains in the way, then we've got a rain shadow over here. And so some of these deserts are influenced by rain shadows. Some of them are influenced by both a rain shadow and subtropical high pressure, and that makes them very dry. And then another reason why deserts can be dry is if you're in the middle of a big continent. So if we look at some of the deserts of Asia, for instance, you're here in the middle of Asia, and there's just not a lot of water nearby, right? You're very far from the oceans, so any air mass that gets to you has already crossed over a bunch of land and might have lost its moisture, or a lot of its moisture. So lots of different reasons or three main reasons for aridity, and that's rain shadow effect, subtropical high pressure, and continentality, being stuck in the middle of a continent. Okay, so we'll talk a little bit about some desert landforms too while we're on the subject of deserts. Now we've talked about wind, and wind is important because desert soils are dry. There's not a lot of vegetation cover, and the dry soils don't stick together very well, so wind can carry that stuff away. But water is still a very, very important factor in the formation of desert landforms, because when we do have rains, they move that loose soil around. So even though rainfall is rare, when it does happen, it does a lot of sculpting of landforms in deserts. And here's a typical sort of evolution of landforms in deserts over time. And this is an example of the basin and range area of Nevada and parts of some neighboring states too. We can see Nevada over here on the left, and Nevada is actually a very, very mountainous state. Most of the state is in the basin and range physiographic province. And what we have is basically a whole lot of normal faulting. So we can see here's a normal fault, right? The hanging wall is slipping down and the footwall is moving up. And so we see we have these mountains up here and our basins in between. And you can see this on the map of Nevada. It looks like caterpillars, marching north to south. And we can see these valleys in between these mountain ranges. Now over time, again, rain falls in these mountains and it deposits a lot of sediment. So the mountains get lower and the valleys get higher until we're left with sort of just the remnants of mountains. Here's an example of the early stages of that. So again, we see normal faults here with the hanging walls moving down. And so we have these mountains with potential to erode. We can see alluvial fans developing here as debris flows come out of these mountains and spill into the valleys. And you can see things like playa lakes, right? There's no place for these lakes to drain because they're in these confined valleys. So any water that comes out can just pool into the lowest spot. After a little bit of time, we can see that the mountains have been eroded lower. More of that sediment has filled up these valleys. We can see that sediment down here. The alluvial fans have coalesced into alluvial aprons or bajadas. And over time, those playa lakes dry up and they become playas. Playas are areas where we have a lot of evaporites, minerals that have left behind after water evaporated. So a lot of salts and things like that. And then in the late stage of this, you can see the topography is really flat now. The valleys have filled up. This yellow color is all that sediment that's come off. And we might just have a few little pockets of rock that were those old mountains. And a word for that is Inselburg, if you have these sort of isolated little rock outcrops. Another interesting thing about deserts and winds, and you've seen this in the dunes video, the size of the sediment is important, just like in rivers. If you have high velocity water, you can move bigger particles, right? And if you have lower velocity water, the particles settle out. Same thing with wind. Wind does not have the same kind of capacity and competence that water does. It can't move really, really large sediments. It can move dust in what we call a suspended load. It can get dust up into the higher atmosphere and transport it very long distances. But anything larger than really, really fine sediments of clay and dust just don't go that far. It's hard to get sand or any bigger particles like that more than like a meter off the ground. But when you do have dust moving around, you get really fine sediments. You get this really interesting feature called desert pavement. So desert pavement forms where all of the sort of largest particles end up being sort of at the surface with smaller particles underneath. So if we have large particles like gravel and cobble and things like that, we get this, this hard-packed surface of rock. And the way this happens is if you blow in dust and small particles from somewhere else, and then you have rain and other ways of moving that sediment downward, the small stuff can kind of move down, and the big stuff just kind of stays on top. It's kind of like if you have a can of mixed nuts and you shake it, and then you open it up, the bigger nuts are going to be on top because the little things like the peanuts and things are going to sink down towards the bottom because they can fit into those little spaces in between. Another interesting thing is that microbes live under the larger pebbles, and they produce little bubbles of gas as part of their metabolism, and those can help kind of make the pebbles more buoyant and shift their position upward relative to this to the finer particles. So over time, what you get is a layer of the coarser stuff, the pebbles and the gravel, and then the finer stuff underneath. And that fine layer can get thicker and thicker, but the other larger layer stays pretty much the same over time. So you get this really interesting formation. And here's just an illustration of desert pavement. It really does look sort of like a paved street with all this pebbles and things up on top, and it's a pretty hard surface. And then the last kinds of desert landforms that you see are caused by windblown sand. So remember, sand doesn't go too high, but it can scour. It can scour exposed rock as it's being pushed along by winds. And so a rock that's been sculpted by sand is called a ventifact. And here we can see a ventifact with different pretty angled sides where the wind is blown at different times and scoured away the sides of that rock. Another interesting feature is called a Yardang, which is fun to say. And again, you can see this rock here, this outcrop, is sculpted by the wind. We can see how sort of aerodynamic the base of this is. And that's because you've got sand scouring the base of that when the wind blows sand across. But remember, sand can't really get more than a meter or so high, even in strong winds. So above this level, we can see we don't see any of that sculpting, and so we see these basically these outcrops called yardangs that get narrow at the base but are larger at the top.